Students, in this video, I am going to discuss cubic spline interpolation. So, what is a cubic spline interpolation? A cubic spline satisfies the following properties. Number one. So, here cubic spline is basically capital F of x. This is a function. Okay. So, a cubic spline f of x satisfies the following properties. Number one. F at any node point xi is equals to small fi. Small fi is basically the data value. That means we have data of this form: x0, x1, x2, xn, and corresponding value of f of x is f0, f1, f2, fn. So we have this data point. So the value of the cubic spline, this, at node point xi is equals to fi. Okay, fi is basically the value of the function f at any xi. Here I varies from 0 to n. Second condition is, on each subinterval xi minus 1 to xi, where I varies from 1 to n, f of x is a third degree polynomial. That's why this is cubic. So there is a third degree polynomial. Third condition, fx, its first order derivative and second derivatives are continuous on open interval ab. Here ab means this x0 is basically a and xn is basically b. Okay. So function, its first order derivative and second order derivative, they are continuous on open interval ab. So now we denote first derivative at xi is equals to small mi, and second derivative of xi, second derivative of f at xi is equals to capital Mi. Okay, so cubic splines do not have the disadvantages of the quadratic spline. What are the disadvantages? We have already discussed. In quadratic spline, we have linear curve either in the first interval or in the last interval. This is one of the disadvantages. So here this type of, and there is a swing. There is a swing, unexpected swing, either in the first interval or in the last interval. So this type of disadvantages are not present in cubic spline. Fine. So now on each subinterval xi minus 1 to xi, we approximate f of x, this function, by a cubic polynomial, which is denoted by this. F of x is equals to pix, a polynomial in the ith interval, which is nothing but ai x cube plus bi x square plus cix plus di. So this is a cubic polynomial where I varies from 1, 2, 3 to n. Okay. Now we have 4n unknowns, because for each I we have 4 unknowns: a, I, bi, ci and di. For each there are total n number of i's, and that's why we have 4n unknowns: ai, bi, ci, di, where I varies from 1 to n, to be determined. So using the continuity of this fx, f dash x and f double dash x, we have the following equations. So we have following equations. First condition is continuity of f of x. So here we have drawn two consecutive intervals, xi minus 1 to xi and xi to xi plus 1. And we have drawn two consecutive polynomials, pix in the interval xi minus 1 to xi and pi plus 1x in the interval xi to xi plus 1. Okay. So now this condition says that function f of x is continuous. Continuous means continuous at xi minus 1, at xi as well as xi plus 1. So we are considering this point. So function is continuous at this point. What is the meaning? Meaning says pi at this point should be same as the value of the function f, small f, given at this point. That means satisfies the interpolating condition. So pi xi is equals to fi, which is nothing but ai x cube plus bi x square plus ci xi plus di. Similarly, this polynomial pi plus 1, if you evaluate at the same point xi, then again the value will be fi. That means this interpolating condition, pi plus 1 xi is equal to fi. But since pi plus 1 is nothing but ai plus 1 evaluated at xi, so xi cube plus bi plus 1 xi square plus ci plus 1 xi plus di plus 1, where I varies from 1 to n minus 1. That means we are not considering the continuity at the function f of x in the intermediate nodes. That's why we have not considered 0 as well as n. Fine? Because if you will remember, here the continuity is discussed in the open interval. We have not considered the endpoints a and b, that means x0 and xn. Hence, we have not included 0 and n here. Fine? Second, continuity of f dash x. What is f dash x? F dash x is nothing but p dash x, polynomial in the ith interval. So continuity at this means what? Pi dash x is equals to pi plus 1 dash x at point xi. So we have this condition, pi dash xi is equals to p dash I plus 1 xi. Evaluate. So just find out the differential derivative. So just differentiate this and this. So we get this equation. Okay. So just differentiate this with respect to x and then put x equal to xi. So we get 3ai xi square plus 2bi xi plus ci. Similarly, just differentiate this with respect to xi. So we get 3ai plus 1 xi whole square plus 2bi plus 1 xi plus ci plus 1. Here I is again 1, 2, 3, 2 and minus 1, intermediate node points. Third is continuity of the second derivative. So again, second derivative of polynomial pi at xi is equal to second derivative of pi plus 1 at xi. So again differentiate this with respect to xi. So we get 6ai xi plus 2bi is equals to this. Differentiate this with respect to xi. So 6ai plus 1 xi plus 2bi plus 1. Again we get 1, where I varies from 1 to n minus 1. Okay. Now at the endpoints, because endpoints are not included here, I equal to 0 and I is equal to n. So for I is equal to 0 we have point x0. So at the endpoints x0 and xn, this is xn. Interpolating conditions give the equations a1 x0 cube. So here what we have seen? We have seen that P1 at x0 is equals to f0. This implies this condition. P1, because in the first interval we have polynomial P1. So P1 at x0 is equal to f0. This implies this condition. Similarly, in the last point for xn, we have polynomial Pn at xn is equals to fn. And this implies this condition. Fine. Fifth equation. So how many equations we have total? From here we have total, from here we have n minus 1 equations, from here n minus 1. So total we have total 2n minus 2 equations. Similarly here we have only single system that, and for I is equal to n minus 1. So total n minus 1 equations from here, so n minus 1. Similarly this is a single system and here I varies from 1 to n minus 1. So total n minus 1 equations, so n minus 1. Here we have total 2 equations, so 2 equations. So how many equations are there total? 4n minus 2 equations. But we have total 4n unknowns. So we need two conditions. Still we need two conditions. So to find the value of 4n unknowns, we need two more equations. So that we have 4n into 4n system of linear equations having unique solution. Okay. So two conditions can be obtained at the two end points as, so suppose f double dash at x0 is m0. Here at this endpoint only value of the function is given to satisfy the interpolating condition, but here the second derivative value is given. Okay, so here second derivative of the function at x naught is suppose capital M naught denoted by P or M naught. Similarly here f double dash at xn is equal to mn, which is q. So if we take m naught is equal to 0, these are the constant values which will be given to you to find the unique cubic spline, and in general they are given as 0. So if we take m naught is 0 and mn is 0, then the spline is called natural spline. Okay, so this is the special spline for which mn is 0 and m naught is 0. Using these two and above obtained 4n minus 2 conditions, that means these two conditions and these 4n minus 2 equations, we can have a system of 4n into 4n and then find the solution of this given system. Okay, let's take the example. So here is the example. So obtain the cubic spline approximation for the function defined by the data x is equal to 0, 1, 2, 3 and corresponding f 1, 2, 33 and 244 with two additional conditions. M at 0, that means at this point m is what? Second derivative. We have already said what is m? M is basically what? Second derivative of the function. Second derivative at 0 is equal to m at this last endpoint, both are 0. That means we are interested in natural spline. Okay, and hence find an estimate of f at 2.5. Fine. So here we have 4 node points. So these are the node points 0, 1, 2 and 3 denoted by x0, x1, x2 and x3. Okay. Now take the spline. This is the spline. So you can see that we have total 1, 2 and 3 partition. So that's why we have total 3 polynomials, P1 from 0 to 1, P2 from 1 to 2 and P3 from 2 to 3. Where P1 is what? This polynomial. P1 is a1x cube plus b1x square plus c1x plus d1 in the interval 0 to 1. Similarly, P2x is a2x cube plus b2x square plus c2x plus d2 in the interval 1 to 2. Then P3x is a3x cube plus b3x square plus c3x plus d3 in the interval 2 to 3. Okay. So now first from the continuity of px gives the following equations. So continuity of this polynomial px is what? This total p1, p2, p3 in single. If you want to denote this polynomial, so we can denote it by px. Px is p1x in this interval, px is p2x in this interval and px is p3x in this interval. Okay. So now this polynomial is continuous. That means continuous at this point x1, continuous at this point 2 and continuous at the point. So basically we are taking the continuity by the definition of cubic spline, continuity in the open interval. So open interval means here and here. We will not consider 0 and 3. They are the end points. So continuity is discussed at the point 1 and 2 respectively. Okay. So P1, this polynomial is continuous at this point. That means x1 is equal to f of x1. What is x1? x1 means 1. So P1 1 is equal to f of 1. P1 1 means just put x equal to 1 here. So we get a1 plus b1 plus c1 plus d1 is equal to f of 1. And from here f of 1 is 2. So 2. This is first equation. Similarly P2, this polynomial is continuous at this point. So P2 at x1 is equal to f of x1. P2 at 1 is equal to f of 1. And P2 means this polynomial. So put x equal to 1 here. So we get a2 plus b2 plus c2 plus d2 is equal to 2. This is second equation. Similarly, this P3 P2 is continuous at this point. So we get P2 at x2 is equal to f at x2. But what is x2? x2 is 2. So P2 at 2 is equal to f of 2. So put x is equal to 2 here. So we get 8a2 plus 4b2 plus 2c2 plus d2 is equal to 33. And now the last condition says that this P3 is continuous at this point. So P3 at x2 is equal to f of x2. That means P3 at 2 is equal to f of 2. This implies put x equal to 2 here. So 8a3 plus 4b3 plus 2c3 plus d3 is equal to 33. Fourth equation. Okay. So this is continuity of the function at intermediate nodes. Now the continuity of the first derivative at x equal to 1 and 2. So just differentiate this function. So the derivative of P1 is equal to derivative of P2 at this point 1. So this implies this P1 dash 1 is equal to P2 dash at 1. This implies just differentiate this and put x equal to 1 here, which is same as the derivative of the P2 at point 1. So we get this equation. Similarly, the derivative of P2 and P3 both are same at the point 2. So this implies P2 dash 2 is equal to P3 dash 2. This implies this equation. Sixth equation. Now the continuity of the second derivative at point 1 and 2. So just again differentiate this 2 times. So the second derivative of P1 is equal to second derivative of P2 at point 1. This implies this equation. Similarly, second derivative of P2 and P3 both are same at this point. Hence we have P2 second derivative at 2 is equal to P3 second derivative at 2. And this implies this equation. Eighth equation. So interpolating conditions. Now we have not considered 0 and 3. So the interpolating conditions at x equal to 0 and 3 give. So here the polynomial is P1. So the P1 at 0 is equal to f at 0, which is 1. So P1 at 0 is equal to f of 0. And with this implies D1 is equal to 1. Okay. So here now in the second condition, P3, this interval, this polynomial, the value of this polynomial at the last endpoint 3 is same as f of 3, which is 244. So P3 at 3 is equal to f of 3. This implies in this polynomial put x equal to 3. So this is equal to 244. 10th equation. Okay. Additionally, we have two more conditions. So m means second derivative. So P second derivative at 0 is equal to m0, which is already given to you 0. So just differentiate this polynomial 2 times and then put x equal to 0. So we get 2b1 is equal to 0. Similarly, differentiate the last polynomial 2 times and put x equal to 3. So we get 18a3 plus 2b3 is equal to 0. Okay. So total we have 12 equation. There are 12 unknowns: a1, b1, c1, d1, a2, b2, c2, d2, a3, b3, c3, d3. So just solve the system of equations systematically. So first we will take equation 1, 9 and 11 and then solve this system. So after solving this system, we get this system from 1st, 9th and 11th. So we get these three equations. Solve this. So we get b1 is equal to 0, d1 is 1, a1 is 1 minus c1. Okay. Now taking second, third, fifth and seventh equation. So we get this system. Solve this system. We get 7a2 plus 3b2 plus c2 is 31. That means we have this system. Okay. Then we will take 4th, 6th, 8th, 10th and 12th equation. So after solving this overall system, we will have the solution a1 is equal to minus 4, b1 is equal to 0, c1 is 5, d1 is 1. Then a2 is 50, b2 is minus 162, c2 is 167, d2 is minus 53. Then a3 is minus 46, b3 is 414, c3 is minus 985, d3 is 715. So ultimately the polynomial is this. P1 is this, which is valid in the interval 1 to 2. Then P2x, this polynomial which is valid in the interval 2 to 1 to 2. And the last polynomial is P3, which is valid in the interval 2 to 3. Now estimate the value. So just estimate f at 2.5 is P3 at 2.5, and this is nothing but the value of the polynomial, which is basically 121.25. Okay, so this is the value. This is the value of the polynomial. Okay, so this is the cubic spline. So now your third unit is over. Now from the next video we will start the fourth unit, that means numerical solution of initial value problem. Okay, thank you.